Thank you, Jonathan, and welcome everybody. Good morning. Brice and I are very excited. This has been 4 years of work from some very talented people at Augment, within our customers, and certainly with the guys at Datamine. So to get here and talk about what we do is it's really exciting. So Augment developed a product called All Movement Policy, or OMP. You'll hear a bit of that going forward. An OMP is an AI-driven 3D glass movement solution developed right here in Perth. So, oh gosh. So what does OMP do? To look at globally open-cut hard rock mines, they all share a common problem: losses, dilution, and mixing due to glass movement. And this is exacerbated if you have selective ores. So when we look at the geologists, and certainly the ones we deal with, they expend an enormous amount of time and effort to optimize their grade control block model, only to see a drill full of holes and blast it into a great big muck pile. And even with existing best technologies, it's very, very difficult to figure out where the ore went in that muck pile. And to quote one of our customers, "What have you done with my metal?" There's a big question that gets asked. So we're going to answer that question. What happens if you have a high resolution block model of your muck pile? And what happens if you can have that in a few minutes after the blast? How will that impact your ability to optimize your dig strings to minimize the ore loss and dilution and the mixing that happens after the blast? Now that's a $10 million question that Brice will be answering shortly. But what we thought to do is quickly take a few minutes to explain how we see our positioning within the marketplace. Now, I have to admit, this is a very stylized diagram. All the geostatisticians in the room, don't worry about the axes, it's not to scale. It just helps to explain how we see the work we've done over 4 years, and to give you a bit of an idea of how we fit into the market. We look at perhaps resolution, because OMP generates hundreds of thousands of vectors. And we're looking at, well, show me the money or the return on investment. And what we've then done is to have a look at the evolution of blast movement monitoring over time. And we've split those into generations, starting off with generation 1, which is the tried and trusted method of polypipe and paint. And of course, that is cheap and cheerful, but not a lot of resolution. I see some good smiles here, and possibly not the best ROI if you look at the consequences of loss and dilution. Generation 2 is electronic, and this was kind of the best and very big step, significant step into truly beginning to understand what happens in a muck pile after a blast. And the technology is well established globally, lots of customers using it, and certainly, as we like to say, in the land of the blind, the one-eyed giant is king. So if you have nothing better, that's definitely a much better solution. But when we talk to users, the common challenges come up is very complex solutions tend to have a total cost of ownership is quite high when you're looking at instruments plus holes drilled and so forth. Nobody wants people on a muck pile, which is not helpful, and the number of vectors or resolution relatively low. So it made a lot of sense when the next generation was the software-only solution, because it took away the Achilles heel of the electronics and then try to deal only with the software. But when we spoken to customers, what they generally tell us is, yeah, that's based on previous thinking or previous technology. Then about 4 years ago, a little thing happened. There was this convergence of deep learning to artificial intelligence and vast, inexpensive compute. And for the first time, it was possible to generate very high resolution estimations of what actually took place after the blast and actually what your Muckpile block model might look like. It is that very high resolution that OMP customers use to make better decisions within minutes after a blast, and it's those decisions that translate into the savings that our customers experience. The other thing about OMP, it's a software-only solution, so it could be deployed remotely or we can go to site. It doesn't require people on a muck pile, which is a great safety benefit, and it's integrated quite tightly within Datamine. So with that, I'll hand over to Brice.
Thank you very much for the intro, Greg. Like Greg said, yeah, we're happy to be here. We've been working really hard on this, and so we're looking forward to share the story with the audience. So like Greg mentioned, we found that geologists put a lot of effort into their grade control model, and it's quite a good representation of the resource. There's a lot of things in there, not just grade, right? And you want to know those. So we took this good data, we took a high-end machine learning algorithm, and we worked out how could we apply a unique vector of movement to every cubic meter within your in situ resource. And that's what I'm trying to give you a window of here, is that this is 100,000 cubic meter volume. There is 100,000 vectors that I've got to try and show you here, which is why we're taking this northern slice and then panning through over the initiation point. So you can see how there are subtle regions of turbulence, there are areas of lift, and when you zoom out, right, it's almost too much information to absorb in one go. When you see the resolution, we're attempting to model how the blast actually transforms your resource. So we started this because we discovered that modern mines have a wealth of good quality data. So as we mentioned, grade control is to a very high standard everywhere we go. And so we take that as a premise. If we were to go to a mine that didn't have good grade control practices, we'd probably recommend Snowden Optero and then keep going, right? And so that is where it starts. But surveys are so frequent now. You can get a survey of every muck pile with 15-centimeter triangles, right? It's a very rich source of data. And especially with the drill and blast teams applying good quality control, dipping every hole, and electric detonators, there's a wealth of good quality data to base an estimation process on. And that's where this all began about 4 years ago. So we applied a methodology, right, in terms of how are we going to solve this problem? How are we going to constrain ourselves? There's always assumptions, right? This is an estimation. We're not trying to be perfect. But what worked out really neatly was to model a muck pile surface at cubic meter levels. And I love looking at diagrams like this one on the screen because you can see the continuous survey of the muck pile dip below and above every cubic meter block. Right? The cubic meter blocks end up having that awkward choice of is there one more here or one less, because it's a very high resolution, right? And that's why you end up with this such a practically perfect fit. And so it practically is the asterisk, right? We're not perfect, but in terms of the assumption we've applied to how we're going to do this, it ends up being a really, really beautiful way to look at it. So because we want to conserve the grade and the tons and every bit of information that's in your grade control model, we applied another methodology, which is called air blocks. So if you start with 100,000 cubic meter volume and the muck pile expands to say 120,000 cubic meters, you've added 20,000 cubic meters of air, right? It's the little spaces between each fragment and how they sit, right? There's no new mass in there. So when we go and model the muck pile, we, in this hypothetical, have added 20,000 blocks in with absent values, where the density is set to 0.00122, right? Because that is roughly the density of air. We wanted to set it as 0, but Datamine didn't like that, so we thought we'd be pretty particular. And the point is, the grunts and the grunt, tons and grade balance at the end of the process. No new metal has been created, no new information of any kind. So because I've explained how we model the muck pile, what our final state is, right? It's a real survey. That's what's waiting in the pit there for you. We also know pretty well what it looked like before the blast because we also survey that as well as your grade control information. But now the drill and blast data becomes that action that has converted your initial conditions into the final conditions. So again, it's an estimation method. And there's so much rich data that can be pulled out of this, right? And so whilst we look at your grid spacing, the timing, the burden relief, and we can take as many variables as your mind has because the machine learning method is dynamic and we make this solution for each mine individually. We actually need information as basic as just timing and deck weight, right? We can be simple in terms of what accuracy is practical to create value for your mine. And although we're very pedantic about making sure we get as loaded values to confirm that the plan is what actually happened, in theory, we can work on planned data for those rare scenarios where you have shifts that are missing and things don't get measured. We're trying to make this estimation process as practical as possible for the mine. So as I described with the air blocks, right, we end up with this really cool high resolution muck pile that is way more resolution than you actually need, right? And so the final process we like to look at is reblocking up to your smallest mineable unit. So this hypothetical example on the screen is a 5 by 5 by 2.5 meter block, right? And so in that volume, you've had all the air blocks averaged out now. So the actual density and tonnage of that block ends up being representative of what you would really get in a shovels bucket. And that also then takes into account how the grade has been diluted, right? Either sheerly by expanding or more likely by the mixing of adjacent material types. And although I've talked about grade quite heavily, like I mentioned, this is your in situ block model. So you could even look at the weathering of a muck pile if you were inclined for such a way. Anything that was in your in situ grade control model is now in this Muckpile Block Model. So we've just sort of introduced the spatial layout of a Muckpile Block Model and now how you can have more precise dig plans to manage loss and dilution. But also from an economic point of view, the way that that blast has diluted your resource and changed the balance of material types is worth assessing in a grade tonnage curve. Now, you'd normally only be able to do this on your pre-blast or your scheduled geology, but you can now actually do a comparison between your pre-blast grade tonnage curve and your post-blast grade tonnage curve, which is the plots I've got up on the screen for you there. So the yellow lines are your in situ pre-blast data, which, as I mentioned, this is a hypothetical model that I'm walking you through for the presentation. So you can see there's a nice big chunk of subgrade I've got at 0.5 and a chunk of high grade at 1, right? That's that step in the yellow line. But when I've redone the grade tonnage curve for a variable cutoff grade, which actually went to a lot of effort, I think the resolution is 0.01 steps, which I just went through to create a nice smooth line, you can see the reality of what dilution has done, right? You can see that smooth line of how it's moving up and changing. And so if we assess that for, again, a hypothetical cutoff grade of 0.2, then what you can see is the difference between the estimate your schedule had pre-blast versus what is actually above that cutoff grade in the Muckpile Block Model is 15,000 tons, right? So it's quite a big amount. And if you do the same assessment on your grade, right, you'll find that the grade is 17% lower than what you thought in situ. And do you want to guess where that 17% went? It went in the 15,000 tons you missed, right? And that's because of how it's diluted. It's not just where was it moved to, right? It's how have adjacent material types changed the material makeup of the smallest mineable unit your loading assets can actually pick up. And finally, again, I'm talking heavily to grade, but if you have a complex set of material types on your mine, you want to also look at other fields. So just as one hypothetical, right, let's say there's a sulfur content that your mill is quite particular about, right? It wants a very specific range of sulfur. No sulfur is not what it's made for, but too much sulfur is a big problem, right? So you've got those fields. You can take that into account and make sure your mine gets what it needs. So this Muckpile Block Model gives a really accurate estimate that we feel can help plug a big hole in a reconciliation chain. So previously, your geological models and your mine schedules have a good estimate of what the mine is meant to operate on, and your mine claim factor is going to have a difference there, which, although the mill assays are your first measured variable of it, you inevitably want to look at a pretty wide moving average of the mill assays to do something representative with that data. So you have this big gap between what was scheduled to go to the mill versus what have we measured is actually at the mill. And you have no way of determining between haulage, loading, and drill and blast how they performed, right, at keeping that metal coming to the mill. And they too often get lost in tons, which is why we've got to change the thinking. And so based on those losses and the dilution I just quantitatively calculated for you through the Muckpile Block Model, you can now attempt to estimate what actually was lost because of the drill and blast design, right? What was sent below the cutoff grade and is no longer recoverable no matter how you process it, right? And give them that accountability for the resource. And that actually gives you a justification to be very firm on loading, right? Load precisely. We've given you a precise model. There's no reason to miss that. And the same thing for haulage. Even if they actually go to the wrong destination, you know what they deposited where, and you can do something about it because you now have that information. So everything I've walked you through, this hypothetical data, we would actually like to make available to the audience. We know what geos are like. We know you like to play and touch and feel. And the reason we called the company Augment is because we don't want to make automated solutions. We want to empower the professionals with their experience and their opinions. So although the grade control data is hypothetical to protect the client that let us use this data, the drill and blast data is real. The surveys are real. The drill pattern and all the loading is real, so that you can get a really good feel for it. But if you go and check the true 3D coordinates of where this blast is, you'll notice that it's conveniently on the Parmelia Hilton, right where we are today. This is something that we'll have available, so you can either reach out to me, Greg, or Jono, and we'll happily share the full Datamine project file, which has both surveys, all the drill hole data, and the three block models: your in situ, your high resolution muck pile, and the smallest mineable unit model. So just to set the expectations right, I want to summarize that what we've developed here is an estimation routine based on a machine learning model of your mine's blasting, and that transforms your grade control model. So there is an implementation process where we go through 4 phases. Site readiness, we're really keen to conduct because we start with a proof of value study and make sure it's right for your mine and that your mine actually will be able to produce value out of it. We move into a configuration, which is where we train your custom machine learning algorithm for your site. And that'll also be where we install the software into Studio RM and do some user training before we inevitably get to the validation. So we have a lot of our own internal machine learning validations we do to make sure this is accurate, but the clients also have their own methods they would like, and we happily facilitate whatever the mine wants to do to validate that this solution works for them, before finally doing some last user training and a go live. So that's what it's like to implement this product. And we're really looking forward to actually taking on some new customers, and we're trying to fill 3 implementation slots in January. So hopefully I introduced a novel concept of Muckpile block modeling, and that's a really interesting idea for you because it is something we want to deliver to geologists to then do markouts and dig plans from with better information. Thank you. Are there any questions?
Yeah, you talked a bit about validation at the end. What kind of things do you do to deal with the results?
So yeah, validation is, for the those playing at home. The question was, how do we validate the procedure and the tool? So essentially, it's how we developed it, right? Machine learning is based on quantify what you want or quantify what you don't want and optimize that. So we have a huge amount of internal processes, and I actually had a slide for this, but because of time constraints, I cut it out. So here's one I prepared earlier. So essentially, what I'd like to just walk you through is the architecture of how the solution works, because that also describes a little bit more about how we validate it. So when we do an implementation, we can start on as few as 15 blasts. That's the minimum critical mass we like to begin with. But the system is designed to essentially optimize over thousands of blasts. It's a big data mechanism. There are deep neural networks, and that's where the longevity of this solution stays accurate for the life of your mine. So we start with a physics engine process that does a continuous simulation. So it'll move blocks in as far as it thinks. It'll throw them. They land on obtuse angles, and we then use that to get the best fit possible to any muck pile that we have measured. So essentially what we're doing is we're fine-tuning a physics process that can reproduce that final result without using it as an input. But as I mentioned, that's a continuous solution. That's not useful for operating mines. So we then move that into a downstream relocation process. So the relocation process is discrete and constrained. A block can only move 1 block forward or 30 blocks southeast, right? And so that process, again, has a different set of validation metrics in terms of its tightness of fit to the continuous vectors that were derived from the physics simulation. So all of this then goes through a blind validation set of data that was never used to develop it, and that is continuously scaled. So as the mine operates, every blast that comes through goes into a validation pool or a training pool, and you get basically this beautiful diminishing returns curve over about a 3-month period of collecting data from a site, which is why we explain the implementation process. And so it typically takes about 2 to 3 months worth of blasting data for a site to do their validation and then be happy with it. So this is our end of validation, but what we've had all kinds of requests, right? Everyone has their own opinions. So we've been asked to compare our model to blast all various types of blast vector instruments like polypipe. Some people are lucky enough to have a visual ore body, so we do a visual comparison. And essentially any metric, like even mill assay reconciliation, we entertain whatever the client's keen on. But this is the driving factor of how we validate.
On the slide, you
talking about 15 data sets with optimized performance 7,000. What is a data set?
The Datamine project that I talked about and I've used this whole way through is what I'm referring to there. So a complete blast instance is the technical term we use, is the grade control model, a pre and post blast survey, and all of the drill and blast data. So the drill and blast data is collars, deck weight emulsion, and timing at minimum.
The survey quality, and we talked about high resolution survey.
Because the block model is a cubic meter block model, we actually can use relatively low res surveys. So anything around a cubic meter of resolution is viable. But what we have found is that almost every mine deploys photogrammetry techniques, and they get such good resolution that we don't really even consider the survey being too low a resolution.
Just want to know, have you had sort of clients use your method to improve your blasting?
Yes, actually. Again, this is another slide I cut out for context, but the score that we give in that grade tonnage curve is information the drill and blast team have never had, right? It's really actually unfair to ask them to look after the metal when they have no measurement of how well did they look after the metal on a blast by blast basis, right? So yes, we actually have a dashboard that essentially comes out of each run through the algorithm. And that information is really useful for the drill and blast team. So we've had a really good relationship with them for that reason.
Just one other question, Rob. Oh, sorry, over there.
Hi. Sorry, I'm struggling to get my head. I've heard about this before, but with that ground truth in, I guess, every blast. So say, for example, you're in a cutback. Let's just say that we're doing a bead blast.
Mm-hmm.
For an example, us using poly or beam members, etc. Most of the time, they won't behave like a typical blast. It will fall off the edge. It will do exactly the opposite of everything in theory. How does the software take that into account with that ground truth?
So what we feel like our most important measurement is that survey of the muck pile, right? So exactly where the highest peak of the heave is. What is the depth of the power trough? Where did the toe fall to, right? These are all very subtle details, but this is the big data sort of end of the spectrum, right? Across thousands of blasts, we have thousands of surveys of pre and post, and all of the grade control information and the drill hole data. So what this diagram is emphasizing is that we would take literally thousands of blasts and use the same method of moving all the blocks to get the highest percentage fit to that muck pile. And what that proves is that whilst we don't need to measure every small little detail like you would previously with a blast vector instrument type approach, we're able to estimate within a practical accuracy how that moves. And this is what I sort of tried to preface at the start. We are not a very accurate simulation. If you want to know where one piece of fly rock's going to end, I'm sorry, we can't do that. But if you would like to know whether this cubic meter block from your grade control model is 2 meters down or 2 meters down and one to the left, that's where we approximate relatively accurately within that cubic meter span. And again, why we emphasize reblocking up to the SMU, right? If your SMU is, say, a 6 by 6 by 6 meter volume, it means in theory, if a block would land 2 meters to the left, 2 meters to the right, it's irrelevant. It doesn't change that SMU's makeup. And so that's the area where when we do these long trainings, we do reconciliation over periods of months, right? The accuracy really starts to converge. And particularly if the mine had a big mill factor to start with, watching the mill factor drop is enough, right? That's really the goal we're there for. It's a good question, thank you.
Just a quick question. With the machine learning and our resolution we're using, we're looking at the environment moving through the profile. Part of your 3 months with collecting big data or project-based data, we are keen in WA, pretty well established where your profile is. So those sorts of default, what's your default inputs, I guess,
so
to your start process in that 3 months?
Yeah, so that's why the grade control model is so important, right? Is we want to take whatever you've got to quantify. It's not just a volume we're shoving around, right? As much as a grade control model doesn't exactly give you a perfect geotechnical summary of how it'll behave, that's where we're relying on the big data aggregation to really make that move. And so, yeah, those different ore types and the material types are very important inputs. And like I mentioned at the start, if the site's grade control practice isn't up to scratch, we don't want to have a risk of our model saying something wrong, because we don't touch grade control models. All what we do is transpose it for you. So yeah, we really hope to refer a lot of people down the Snowdon Optero path when we see it's required.
So, I guess in terms of the learning, whether it's a training or an audit class, do you guys are part of that, I guess, process in terms of?
So the user training or the algorithm training? So the algorithm training is actually quite an automated system. So every blast you run through the system goes into a data pool, and then we have our own systems of whether that's a training or a validation set. But essentially, we actually curate validation sets very detailed to make sure we've got every sort of representative scenario covered in the validation set. And that is something we're very transparent about, right? Because we know people tend to think of this as a black box, which is why we're trying to dispel that, right? It is a deterministic system, and it's got a lot of validation in it.
And sorry, just one more question. You were saying, what, 2 to 3 months of learning. So what's your computation time then for each blast? And are we talking server farms here, or are we talking
So our preferred method of deployed is to a server on-site and on-premise deployment. But because we know what the requisition departments are like, we also have a cloud offering, which is available from day one very easily. So you can have either a cloud offering or an on-prem offering. But the training process is big and complex because it's development. The deployed process takes about 10 minutes, right? So as soon as that post-blast survey is available, 10 minutes later, you have a Muckpile block model. Good question.
I have one question. Can this software actually deal with the multiple blasts? Like you have one blast today and tomorrow another blast moves into it? How do you reprocess existing stuff?
So if there's a survey in between them, it's really easy, right? So if you were able to do a cut blast where there was enough time to survey that volume, then how the next blast moves onto that volume is really straightforward.
Generally don't.
Sorry?
Generally we don't have time. So
correct. So in that scenario, we actually would use one of our other products. So we have another product which is called a Muckpile prediction routine, MPR, because everyone loves the acronyms. And basically the way the Muckpile prediction routine works is it takes drill and blast data and your in situ grade control model and a pre-blast survey and predicts a post-blast survey. And so the idea there is that what you've described is one of the scenarios as to why that solution was required. But the other reason is that it's the exact same set of data, right? The same data we've been collecting this whole time. We're just changing the supervised answers of the algorithm to the surface. So that's how we would handle that scenario, is we would actually predict the survey you couldn't measure and then use that to constrain the volumes.
I have one more question. So these calculations is based on the 1 cubic meter vectors, or you actually doing the calculations of more such small pieces and then summarize them into 1 cubic meter blocks?
No, the 1 cubic meter was ridiculously high resolution in our opinion. The fact that you want more makes me wonder what your ore body looks like. So it's and that's why the SMU scale is what we're trying to move up to. So essentially one SMU block should be almost hundreds of smaller 1 cubic meter estimates.
To be honest, we are using another solutions doing similar things, and then we used to use 1 cubic meter, stuff it quicker, and then we figured out additional 12% unplanned dilution happening. So we started actually using as a half meter blocks as a standard, which is around 7% external dilution, which I done another one 0.25 meter blocks, gives you almost perfect, represents your real boundary. Because when you do the storms and grade graphs, mathematically on the computer they're fine, but it's actually in 1 meter cubes is actually big enough. When you mark out on the ground, you give you additional meter unplanned dilution on top of your blast dilution. So there's a geometrical issues happening with 1 cubic meters.
Yeah. Okay. That's good feedback. Thank you. We would like to go high resolution. It's definitely something we think about, but for where we're at now and the mines we're looking at, the 1 cubic meter is working for us.
And then this can only move the blocks, or can you move wireframes on strings as standard?
So what we are trying to do with all movement policy is give you a Muckpile block model. That is our service. And whilst we definitely can help converting that into a dig plan and optimizing those things, what our goal is to do is to leave that in the hands of the customer and trust that they like that freedom.
How does it deal with things like voids?
Underground voids are a very fun challenge, but the answer is very well. So like I mentioned with the air blocks, the premise is that they have to be surveyed voids. If they're unsurveyed voids, then I'm sorry, there's just nothing we can really do about that. But again, it's why we take so much confidence in that Muckpile survey, because if there was an unsurveyed void there, the Muckpile will be different, right? It will show that effects. And so whilst there may be a bit of error because you thought there was grade there, when in reality it was a hole, in terms of movement, we feel like we handle that very well. That was a lot of questions. Thank you.